All right, class, settle in. Today, we're going on a pretty wild journey. We're going to start with the strangest, most counterintuitive rules in the entire universe. And we're going to end up understanding how the very device you're watching this on right now actually works. Believe it or not, it all comes down to quantum mechanics. So, let's dive in.
So here's the game plan for today. First, we'll get our feet wet with the basics of modern physics. Then, we'll look at the specific rulebook that particles, especially electrons, have to follow. We'll see how those strict rules naturally create something called the Fermi level. And then, this is the really fun part, we'll see how we can hack that concept to engineer materials and build our modern world. First things first, to understand something as seemingly simple as a transistor, we have to start with the truly bizarre reality our universe is built on. So let's take our first step into the strange world of modern physics. When you hear the term modern physics, what we're really talking about is the rule book for the universe that came after Newton. Your classic Newtonian physics is fantastic for predicting the arc of a baseball or the orbit of a planet. But when you zoom way, way down to the level of atoms and electrons, those classical rules completely fall apart. For that, you need a whole new set of instructions: quantum mechanics. Okay, so in the world we see every day, things are pretty straightforward, right? A bowling ball is a particle. It's in one specific place at one specific time. A ripple in a pond, that's a wave. It's spread out. They are two totally different kinds of things. An object can't be both. Or can it? Well, it turns out it can't. Welcome to the first, and maybe the most mind-bending rule of the quantum world: wave-particle duality. At these tiny scales, something like an electron can behave like a particle or like a wave, depending entirely on how you look at it. It can be one or the other, but here's the kicker: never both at the exact same time. And this weird, strange idea, this is the absolute bedrock of everything else we're going to talk about today. Okay, so if everything is so fundamentally weird, how do we predict anything? How do we build things that actually work? Well, thankfully, even all this quantum weirdness follows a set of rules, and I mean really strict rules. We call them particle statistics. So, you can basically group particles into three families, each with its own rulebook. You've got your classical particles, like molecules of a gas. They follow Maxwell-Boltzmann stats. Then you have particles like photons, the particles of light, which follow Bose-Einstein stats. But for us, for electronics, the only one that really matters is that last one, Fermi-Dirac statistics. This is the rulebook that governs electrons, and it has one single, absolutely unbreakable law. And folks, this right here, this is the whole ballgame, the Pauli exclusion principle. Think of an atom like an auditorium with very specific assigned seats. Once an electron takes a seat, which is just a specific energy level and spin, no other electron in that entire system is allowed to take that exact same seat. It has to find a different, usually higher energy seat. This one single principle is why atoms don't just collapse in on themselves. It's literally the reason we have chemistry. Okay, so think about that. If every electron has to find its own unique seat, and they fill up from the bottom, starting with the lowest energy, what happens when you've placed your last electron? Well, you end up with a natural full line, a ceiling. That highest filled energy level is so critical it gets its own special name, the Fermi level. So to be super precise about it, at the absolute coldest anything can possibly get, we're talking absolute zero, the Fermi level is like a sharp line in the sand. Every possible energy state below that line is 100% full, and every state above it is 100% empty. It's a perfect, clean cutoff. And of course, physics being physics, there is a stunningly elegant piece of math that describes all of this. Now, don't panic, you're not going to have to solve this. Just take a moment to appreciate it. This function is the mathematical key to everything. It gives us the precise probability of finding any given seat, any energy level, occupied at any temperature. So what does that equation actually tell us? Well, let's look at the simplest case, absolute zero, when temperature is zero. The math spits out a really simple answer. If the energy level you're looking at is below the Fermi level, the probability of it being filled is 100%. If it's above the Fermi level, the probability is 0, a perfect step. But what happens in the real world, where things aren't at absolute zero? What happens when you add a bit of heat? Well, that perfect sharp step gets a little bit fuzzy. A few electrons get enough thermal energy to jump up to higher empty states. And right smack dab at the Fermi level, something amazing happens. The odds of finding an electron in that seat become exactly 50-50. And that becomes the practical, real-world definition we actually use for the Fermi level. All right, so now we have the rules of the game. We know about electrons and their assigned seats, and we know about this energy ceiling, the Fermi level. Now we go from being physicists, just observing nature, to being engineers who can control it. This is where we learn to hack materials to give them the properties we want. This is the birth of solid-state electronics. So let's start with a nice, pure crystal of silicon. Think of it like a perfectly organized community where every silicon atom holds hands with 4 neighbors, nice and stable. But what if we sneak in a few atoms of, say, phosphorus? Phosphorus likes to hold hands with 5 neighbors. So when it sits in the silicon crystal, you have 1 extra electron that's left over with nowhere to go. This whole process is called doping. And since we've added negatively charged electrons, we call this an N-type semiconductor. So where do all these extra homeless electrons go? Well, they occupy a new, high-energy level all by themselves, just shy of what we call the conduction band. You can think of the conduction band as the express lane for electrons. If they can get up there, they're free to move around and carry a current. By adding these extra electrons, we've pushed the whole Fermi level up, way closer to that express lane. It now takes way less energy to get things moving. We've made it a much better conductor. Now, let's do the exact opposite. Instead of phosphorus, let's dope our silicon with boron. Boron only wants to make 3 bonds. So when you stick it in the silicon crystal, you've created a vacancy, an empty spot where an electron should be. We call this a hole, and since it's a lack of a negative charge, we treat it as if it's a positive charge carrier, and that gives us a p-type semiconductor. And you can probably guess what happens to the energy levels now. These new holes create an available energy level just above the valence band. That's the band where all the electrons are normally locked in place. This pulls the overall Fermi level down. Now, it's super easy for a neighboring electron to just hop over and fill that hole. But when it does, it leaves a new hole behind. So from the outside, it looks like the positive hole itself is moving through the material, carrying a current. Okay, everyone, this is the grand finale. We have our N-type material loaded with extra electrons. We have our P-type material full of these holes. We've hacked them both. So, what happens if we just stick them together? Well, we create the single most important electronic device ever invented, the p-n junction. It's really as simple as it sounds. On one side, you've got the p region, full of mobile positive holes. On the other side, the n region, chock full of mobile negative electrons. The absolute instant they make contact, nature does what it always does. It tries to find equilibrium. Almost instantly, a bunch of those free electrons on the n side see all the inviting empty holes on the p side, and they rush across the boundary to fill them up. But here's the thing, this mad rush only happens in a razor-thin zone right at the junction. In that tiny area, the holes are now filled and the extra electrons have found a home. The area has been depleted of any mobile charges. We call it the depletion region. And this depletion region, this is the secret sauce. Because all those negative electrons moved over to the p side, you've now created a powerful, built-in electric field right at that junction. It's like a little battery inside the material itself. And this field acts as a barrier, a wall, that prevents any more electrons from just wandering across. The process stops itself. And that's where we'll leave it. We've gone from the weirdness of wave-particle duality, through the strict rules of the Pauli exclusion principle, all the way to engineering a microscopic one-way street for electricity. Think about it. This one little device is the fundamental building block. It's the simple diode that makes your phone charger work. And if you stick a few of them together in just the right way, you get a transistor. And with a few billion of those, you get the processor that powers our entire digital world. It all starts with that strange little rulebook for the universe.